now I will start the discussion for today's class. Okay. So up until today, we have discussed the internal force, which is happening at one particular point, and the internal force distribution and moment distribution as well. So this is the discussion on the internal force and moment diagram. Okay, and yesterday I already started discussion on this and how to create the internal force diagram and moment diagram. Okay, so this is one of the problem example that I discussed yesterday, and this is the second problem example that I discussed yesterday. Okay, and as you can see here, okay, whenever we have a concentrated load, okay, we tend to have whenever we have a concentrated load, here, we tend to have a constant internal force until it reaches the next discontinuity. Yeah, then there will be another jump here. Okay, another jump which is the same as the value of P there. Then this one as well, it will create another jump which is the same as the value of P there. Okay, so whenever we have a concentrated load, right, in the shear force diagram, there will be a jump there. So you can see it because of P over 4 on the left edge, right? There was a jump here to minus P over 4 there. Then due to this particular P there was a jump here where the jump is the total jump is P, because it's jumping from minus P over 4 to 3P over 4. Then due to this particular load 2P there will be a jump here which is 2P. The jump will be 2P because it's jumping from 3P over 4 to minus 5P over 4. Same at the last location at the right edge, because of 5P over 4, there will be a jump there which has the value of minus 5P over 4. So the jump will be in the same value as the concentrated load there. Okay. Up until now, is there any question about this internal force? Yes. Yes.
Hello.
Yeah.
I want to be honest, I want to ask for number 2 on yesterday question, but there's no time.
Okay, so this one, yeah. What's the
yes. Is there the slide where
this one, right?
the work? Yeah.
Oh, you mean this one? Okay.
Yeah. I want to ask. In the moment, there is 1.5 kilonewton, the distributed force. For the distance, what should we put in there? There's you put 1.5 times 4 minus x times 2 minus x over 2.
Okay.
From where?
So this particular problem, right?
Yes.
why I do it that way, right?
Yes.
Okay. After this, I will explain to you. But before that, I will highlight another jump here. Okay. So as you can see here, as in my previous explanation, there is 2 kilonewton concentrated load there. And on the left edge, you can see that in the shear force, there is a straight jump from 0 to -2 kilonewton. Okay. And the same thing will not be happening on the edge of the distributed load. As you can see, there is no jump there. It's still at -2 kilonewton, but distributed load will create this kind of distribution because it's linear. Because it's constant here. The distributed load, the shear force distribution will be linear there. Okay, and at the end, as you can see, there is a 5 kilonewton shear force there. So as you can see as well, at the right edge, there is a jump from 0 to -5 kilonewton. So the amount of jump is still 5 kilonewton. So you can see there how to detect whether your answer is correct or not. So you can see from the jump whether the jump is exactly the same as the shear force that we have at each location. So you can check that. Here, the jump must be the same as this one. Here, the jump must be the same as this one. Okay, the same jump will be happening as well when we have concentrated moment. Okay, as you can see, concentrated moment, we have one concentrated moment at the right edge, 11 kilonewton meter. That is why we have here at the right edge jump of 11 kilonewton meter from 0. Okay, if we take a look from the right edge, it is jumping from 0 kilonewton meter to 11 kilonewton meter. This one. So there is one of the way to check whether our calculation is correct or not. Okay, and just now, Rizky asked me, how can I calculate for the sigma moment at the left edge here? And the results of the calculation is like this. Correct, Rizky?
Yes, Pak.
Okay, now I will discuss it one by one. Okay. The sigma moment that we do here is the sigma moment at the left edge. So this particular point. Okay, and the left edge there has distance of 4 minus x. Okay, why 4 minus x? Because actually, if we want to do the cutting from the left, like this, right? This is the side that we're supposed to be drawing. Okay, but instead of doing so, we draw it this one, the right side of the cut, instead of the left side of the cut. If we want to draw the left side of the cut, okay, the drawing is supposed to be like this. The free body diagram is supposed to be like this. One, zero. Okay, and of course we will have a shear force and we will have a moment. So that's the drawing that we will give there. Okay, that we will get there. and the distance here is supposed to be x. Okay, Rizky? This
Yes,
is
Pak.
the case if we draw the left side of the cut. And this one is the case where we draw the right side of the cut. The right section and the left section. This one is the left section. This one is the right section. Okay? Rizky, do you get it?
I get it, Pak.
Now, if for the left section, we define, from the beginning, we define that x is actually the distance from the left edge, right? Okay? From the beginning,
Yes.
we define that x is like this, right? Distance from the left edge, right? This one. Correct, right, Rizky?
Correct, Pak.
Yeah. So, this particular distance is x. Correct, right?
Correct.
Now, if that one is x, how about this one then? This particular distance?
Which one, Pak? Sorry.
This one. From
It's 4
this,
minus x.
Yeah. 4 minus x, right? Correct, right? Because the total length of the beam is 4 meters.
Yes.
The total length of the beam is 4 meters. So if the left section is have x length of x like that, so the right section supposed to have a length of 4 meters minus x. It's logical, right? Rizky?
Yes.
Okay, so we agree that the length here is 4 minus x because we do the sections from the right. So the section is 4 minus x. Now, how to calculate the moment from this left edge? That's the question. Okay, so we want to calculate the moment from the left edge. Okay, if we want to calculate the moment from the left edge, there are several things that we're supposed to consider. This is the first one, m. This is the second one, 11 kilonewton meter moment. And then we have a shear force, 5 kilonewton. And the last one is supposed to be the distributed force, 1.5 kilonewton meter over the length of 4 minus x. Correct, right, Rizky?
Correct,
Phi
Pak.
here, we don't have to consider phi because phi has moment arm length of 0, right?
Yes.
Okay, so those 4 are the things that we're supposed to consider. So m, I assume from the beginning that m, the moment clockwise is positive. So m is there. Then I want to calculate the moment due to the 5 kilonewton. So 5 multiplied by the moment arm. The moment arm there is supposed to be 4 minus x, and the direction is counterclockwise. So it's minus 5 multiplied by 4 minus x. Okay, Rizky?
Okay, Pak.
And then 11 kilonewton meter clockwise, positive.
Yes.
Okay, and the last one is the moment due to the distributed load. Okay, the moment due to distributed load. Remember, when we talk about distributed load, okay, in order to calculate the effect of the distributed load, we have to convert it to force first. How we can convert it to force? Okay, we have to multiply the distributed load with the length where it's applied, right?
Yes.
Although the actual length is 2 meters here, but because here we only draw the limited free body diagram, which has the length of 4 minus x. So this will be our length. Do you get it, Rizky?
I see. Okay.
So 1.5 kilonewton meter multiplied by 4 minus x, it will be our representative concentrated load.
Yes.
Okay, then the centroid is here, exactly in the middle.
Yes.
So I can replace the distributed load with a concentrated force at the centroid. Okay, right? The concentrated force there is supposed to be 1.5 multiplied by 4 minus x, correct, right?
Correct, Pak.
Okay, then after that, I multiply it again with the moment arm, right? Because this is what we talk about here is moment.
Yes.
So the force multiplied by the moment arm. The moment arm, because the centroid is exactly in the middle, what is the moment arm there? It's supposed to be half of this, right?
Yes, 2 minus x.
Yeah, 2 minus x per 2.
Yeah.
So that's why, because this is the moment arm, so that's the last multiplication. 1.5 multiplied by 4 minus x is the force multiplied by the moment arm, 2 minus x per 2. You get it, basically.
Pak, so in this particular equation, you can center the distributed force first, but in respect to x for the distance.
Yes, we can do it that way. But you cannot do it like this. What my warning from before is, from the final calculation of the distributed force, you cannot just think about the distributed force as a concentrated load at 3 meters from the left edge, because the distribution will not be correct later, or 1 meter from the right edge. So the distribution will not be correct there. So whenever we have a free body diagram, okay, we can do the representative concentrated load of a distributed load. We can do that, but it's for each free body diagram. Do you get the risky? So for example, if we have drawn this particular free body diagram, then we can assume that we have a concentrated load at its centroid like this, but it's just for this particular free body diagram. It will not be applied for other free body diagram. So another example is like this. Okay, I want to use this particular free body diagram. Okay, for this particular things, then this is my representative concentrated load at the centroid. Okay, Rizky?
Okay, Pak.
Okay, the distance there is slightly different from this. Okay, x is from the left edge to the right edge. Okay, from the right to the right cut. Okay, and the distance here is supposed to be 2 meters, right?
Yes.
Okay, so in that case, then the length here, it's supposed to be x minus 2 meters, right?
Yes, exactly.
Okay. And the length there is supposed to be x minus meter, and the centroid, it's supposed to be 2 meters plus x minus 2 meters divided by 2. Okay, Rizky? That's the length until it reaches the centroid from the left edge.
Okay. Yes.
Do you get it, right?
Yes, I get it.
Yeah, because from the left edge to the initial of the distributed is 2 meters, and then
Yes.
half of the length of the distributed load, it plus half of the length of the distributed load, it will be the location of the centroid. Do you get it, right?
Yes.
Yeah,
Get
something
it.
like that. So whenever we have a okay, anyway, whenever we have the distributed load, it's okay. We can consider that as a concentrated load, but only for each free body diagram. You cannot assume it as concentrated load, generalize it as concentrated load. Then after that, it will go to the next free body diagram like that. No, it cannot. But take a look at the concentrated load only for each free body diagram. So the simplification, you can only do it for each free body diagram.
Pak, jadi cara paling aman kita potong di mana ada section yang isinya distributed force ya?
Yep, yes, correct. So
Okay.
you cannot draw it like this. For example, right? If from the beginning you assume it as a distributed load, right? From the left edge, this is what I'm afraid of. From the left edge, you cannot draw it like this. 2 kilonewton, and then the distributed load there, 1.5 multiplied by 2, 3 kilonewton meters. 3 kilonewton, sorry. The distance here is 3 meters. Then this is V, this is M. This one is the wrong free body diagram. Why is wrong free body diagram? Because you take over the concentrated load, the simplification of the concentrated load from the initial boundary condition to the next boundary condition. You cannot do that. Okay, when you cut, okay, always assume you cannot simplify the location of the free body diagram. Sorry, when you cut, you cannot simplify the distributed load. So you have to draw the distributed load. So for example, I cut it here. So I have to draw the distributed load. Then after I draw the distributed load with the exact length and the exact distance, then after I draw the free body diagram, for example, like this, then I can do the simplification to get the to put the constraint load to represent the distributed load, but not from the beginning, putting 3 kilonewton meters there at the distance of 3 meters from the left or 1 meters from the right. In that case, if you just putting it like this for all the free body diagram, in that case, the assumption is not it's a distributed load, but it's concentrated load, 3 kilonewton meter. Do you get it, Rizky? Hello?
Yes, Pak.
Good. For the rest, for the rest of the student, do you get my explanation?
Oh yes, sir.
Good. So the simplification can be only performed after you draw the free body diagram with the distributed load. After you draw the cut, the section free body diagram with distributed load. So the simplification can only be performed at the end, not from the beginning. Okay. Any other question?
Hello, sir. I'd like to ask.
Yeah, who's this?
Matthew, sir.
Okay, yes, Matthew.
Will it be easier if we cut it from the right?
Oh yes, of course.
There's only
It will be easier to cut it from the right. That's why my yesterday's example is to cut it from the right as well, because it's only one part of the distributed load that we will need to handle, right? Yes, correct.
Yeah, but then why did you cut from the left to count that quadratic form? Quadratic.
Yeah, this one is from the left. Sorry, this one is from the right.
Oh no, I meant cut from the left. Wait, no. So that there's no the external force is only 2 kilonewtons.
No, you cannot do it that way, because the equation supposed to cover from 2 meters shear until 4 meters shear. So like it or not, the cutting must cover the distributed load as well. Do you get it?
Why is it not allowed, sir?
So if you just cut it here, Matthew, if you just cut it here, so from the 0 to 2 meters, right? As you just cut it at 2 meters, what you will have is just the equation for this particular point at 2 meters. So if you just include the 2 kilonewton load, so it means just the same as the first cut then, which will be okay for x equal to 0 until x equal to 2 meters. Okay, the distributed load, sorry, the moment, the internal force and internal moment diagram is actually how we need to draw the internal moment and internal force diagram is because we need to make sure that the whole beam is represented by the internal shear force diagram and internal moment diagram. Okay, so the whole beam is supposed to be represented there. Okay, the whole beam is supposed to be represented there. So from x equal to 0, this one, until x equal to 2 meters, it can be represented by the first cut, by this particular free body diagram, because we assume it's x there. And from x equal to 2 meters, this particular point, until 4 meters, this particular point, okay, it can be represented by the second cut there. Okay, the second cut, we can represent it from the left side of the cut or the right side of the cut. It is much easier to draw it from the right side of the cut. Why? Because we need to draw the effect of the distributed load like this. Okay, if we want to draw from the left side of the cut, okay, as what I told you before, it will be like this: 2 kilonewton. Then there will be a distributed load here, 1.5 kilonewton per meter. And then this is the internal shear force and internal moment. And the distance there, it will be difficult as well. Right? The distance there, it will be x, yes, correct. Then the length of the distributed load there, it will be 4 meters, sorry. This one, it will be from this one, 4 meter, x minus 2 meters. From this to this is x minus 2 meters. Okay.
Okay,
So,
sir.
basically it's like this. Whenever we do the cutting, okay, we have to make sure the cutting, the section, can represent a certain part of the beam. So, for example, the first cut, it represents the this particular shear force diagram and this particular moment diagram. The second cut in this shear force diagram will represent this part, and in the moment diagram, it will represent this part like that. So we have to make sure that the shear force and the moment, okay, are represented in the whole beam length. You get it, Matthew?
Yes, sir. Thank you, sir. I have another question.
Yeah.
What if, let's say there's a beam and then there's an external force, right?
Mm-hmm.
how do you find the internal forces directly where the force is exerted, the external force is exerted?
Oh, so you mean this like this, right? When we have
We cut at
1p, 2p like that, and the results is there will be a jump there from minus p over 4 to 3p over 4 like that, right? So what is exactly the value at this particular point, you mean, right?
yeah.
Okay. The answer is there are two values there. Okay, because there is a jump there, and actually, the discussion for that one is quite long because actually this one is like a simplification. This particular distribution is actually kind of a simplification, Matthew. And for statics, this simplification is still okay. So when you are asked what is the value of P, what is the value at exactly where the load is given, okay? The answer is if just slide to the right, this is the value. If it's just slide to the left, this is the value. Okay, the exact value where the load is given actually is unknown. And actually it's not unknown, but I mean, it's more advanced topic. So just knowing what is the value slightly to the right and slightly to the left is supposed to be okay. So sometimes what you need to do is just to find out the value which is more critical. So for example, this one is more critical than this one because it's bigger. 3p over 4 is bigger, so we choose that one. Okay?
Okay, thank you, sir.
But do you get my explanation on where we're supposed to put the cut? So we are not supposed to put the cut in the middle of the, so like this, just in the intersection like that. We are not supposed to put it there. Because if we just put it there, what you will get is just the value of the internal force and internal moment at this particular location. What we're trying to find is the distribution. So we're supposed to find the section which can represent the distribution. You get it?
Yes, sir.
Okay. One more thing. For any of you who still confused about where we're supposed to cut and where we're supposed to put the cut and how many cut that we're supposed to use for certain problem, for example. Okay. For that particular case, right? I think I already uploaded in the MS Team. Wait a minute, let me share. Okay. Can you see my slide, Matthew? Yeah, sorry. Yeah, my sharing screen, Matthew.
Yes, sir.
Okay. Try to watch for this particular video. This is the explanation on how to determine the number of section and the section location. It's from last year class, but it can help you to deepen your understanding. This is for all of you guys. Okay, this is for all of you guys. So basically, I put several videos there in my YouTube channel. Okay, and you can find the link here. Determining the number of section and section location. And if you want to deepen your understanding as well about the explanation on the internal force and moment distribution, you can watch this video, this 4th video. Okay, Okay, Matthew?
Okay, sir. Thank you, sir.
For the rest of the class as well, please watch the video that I post in the MS Team, the video link that I posted in the MS Team, because I believe it will deepen your understanding.
Sir, I want to ask.
Yes.
This is about the section that you do before.
Mhm.
If you section a distributed force, is it gonna divide the distribution force too, or it will stay the same 1.5 kilonewton? Like I mean,
No.
you
One
section it
point five
at the
kilonewton per
middle, right?
meter is the value of W. It will not be changed whether you cut it anywhere in the distributed force.
Oh.
Remember, in order to calculate for the representative concentrated force, you have to multiply. You have to multiply this. Okay, you have to multiply that 1.5 kilonewton meter with the length of the distributed force, right? The same as this one.
Yes.
1.5 kilonewton meter multiplied by 4 minus x. 4 minus x there is the length of the distributed force.
So the distributed force is bergantung lebih ke jaraknya ya, Pak?
Yes, correct.
So something like a function of this function of distance, yes, sir.
Yes, correct. That's why it is important to define the distance here in the correct way. Just now we put this as x like that, and the distance from the left edge to the boundary of the distributed force is x minus 2. That's why the that one, this one is not x minus 2. Sorry, x minus 2. So this one is correct, right? This one is 2 meters, and this one is x. So this that one is x minus 2, and the distance from here to here is x. Okay. Sorry, x minus 2 is actually not that one. I put it the wrong way. X minus 2 is supposed to be this. This one is x minus 2, because this one is 2 meters. Okay, the length is x minus 2. Correct, right? The length is x minus 2. That's why you have to determine the this correctly, because the distance there, like this as well, is very important. Okay.
Okay, sir.
Any question about this? And remember, okay, one more thing. When we have a distributed load, right, like this, constant distributed load. Okay, when we have a constant distributed load like this, okay, the shear force will be linear, always like that, and the moment will be quadratic, like what you see here. The moment distribution is quadratic. There, the shear force is linear, so it's always like that. Later, when you have a linear distributed force, the shear force will be quadratic, and the moment will be to the power of 3. So the distribution is always like that. Okay. Any question here before I continue with this one? This one is.
I want to ask, sir.
Yeah.
If the problem is about a constant internal force in a certain location, can we change the distributed force into a concentrated force?
Sorry, Can you repeat again?
If the problem is about an internal force in a certain location, can we change the distributed force into a concentrated force?
Yes, but that problem is actually the previous case that we discussed, right? The internal force and internal moment at certain location, so only at one point, right? You mean?
Yes, sir.
Yeah, in that case, just do the section at that particular point, and you can assume after you draw the free body diagram of the section, you can replace the distributed force with the concentrated force, but always replace the distributed force to concentrated force after you draw the final free body diagram. Do you get it?
Yes, sir, I get it.
So, for example, I want to draw I want to check this particular point, 3.5 meters from the left edge. This particular point, you get it, right? This one. So I can put this particular section and draw the free body diagram there. For example, my free body diagram will become like this. Okay. So I will still draw the distributed force first. Okay. And the length from here to here is 2 meters. The length from here to here is 1.5 meters. So this is the free body diagram, right?
Yes, sir.
Okay. Then after you draw the final free body diagram like that, then you can simplify. Oh, the centroid is here. So this one is supposed to be the representative of the concentrated force. The location is supposed to be 0.75 meters from the right cut. Okay, or 2.75 meters from the left side, left edge, like that. Okay, you get it?
Yes, sir, I get it.
Yeah.
Thank you, sir.
But this one is for it's not for the distributed force. Okay, this is just for the internal force and internal moment at certain location.
So we cannot do that way for diagram problems, right?
Yes, correct. You cannot do that for diagram problem. For
Okay,
diagram
sir.
problem, the representative cut you're supposed to put it in certain location to represent a distribution for certain line, like that. And the videos on how to determine that I already posted in MS Team. Okay, you get it?
I get it, sir. Thank you.
Any other question before I continue with this problem example and this one? Any other question? No? Okay. In that case, I will continue with this particular problem example. Yesterday, the one who helped me, it was I think the last person to help was who? I forgot.
I think it was Risky, sir, who last helped you.
I don't think that is risky. Shabina, I believe, right? The last person to help me was Shabina, right? Correct, right, Shabina? Hello, Shabina. Hello, Shabina. Seems like Shabina is not here. Okay then. Anyway, now I will point out another person to help me. Darian Patrick.
Yes, sir.
Okay, please help me to solve for this particular problem, Darian Patrick. What's the first thing that we're supposed to do in order to solve for this particular problem, Darian?
Find the resultant of the distributed force.
That's the second one. The first one
Oh.
is to draw the free body diagram, which include
yes.
this and this, right?
Yes.
Which include this and this. Okay, so let's try to draw the free body diagram of the beam. Okay, there is a distributed force. Okay, at A, thrust bearing and journal bearing. Okay, a Y, BY, BX. Then what's we supposed to do next then in order to solve for AY, BY, BX?
Sir, may I just ask before we continue? Why is there only AY in the A point?
Because there is two type of bearing there. The one of it is thrust bearing, and the other one is journal bearing. Okay, the type of bearing
okay.
will determine whether it has only one reaction force or two reaction force. But don't worry about this because you the topics on the journal bearing and thrust bearing is hasn't given we haven't given it to you yet. Later, when we have a problem like this, we will not put it as a thrust bearing or journal bearing, but we will put it as pin or roller like that. Okay. If we put it as thrust bearing or journal bearing, okay, most likely we will tell you that, oh, thrust bearing is this kind of bearing, which has this kind of a reaction force. Journal bearing is this kind of bearing, which has this kind of reaction force. So you don't have to worry about it. Okay?
Okay, sir, okay.
Okay, Darian. So what we're supposed to do next?
Find the resultant, the distributed force.
Resultant for the, okay. We have to find the representative concentrated force, right?
Yeah, yes. I meant.
Okay, this one, okay. I think I will put it as different color. Okay, so this one is the representative distributed for a concentrated force. Okay, what is the value there for the representative concentrated force?
So it's times
120 pound per feet multiplied by 12 pound per feet divided by 2, right?
yes.
The area. So 720.
720, right? Yes.
Yeah, 720 lbf. It's there. Okay. And then we can calculate for AY, BY, and BX. Right?
Yes.
Sigma fx equal to 0. We have BX equal to 0.
Equals to 0.
Yep. And then sigma moment at A equal to 0. But you have that?
BY times 12 minus 720 times, I believe it's
2/3 from the zero, from the zero distributed force, or 1/3 from the maximum distributed force.
So times 8.
Yes, correct. Times 8 feet equal to 0. So what you get for BY?
480 pounds.
480
80, yes.
lbf. Then using sigma fy equal to 0, what you have here?
Y plus BY minus 720 pounds.
AY plus
Plus
BY minus
minus
720 lbf. Okay, pound force equal to 0. dy there is supposed to be 440, 480, right?
Yes.
So
AY is 240 pounds.
240. Yeah, 240. Yes, correct.
Yes.
240. Okay. So we have all the constraint load there. Okay, all the reaction force there. Okay. Then, in order to draw for the distributed force and distributed internal distributed force and internal moment, what we supposed to do after that? How many sections that we supposed to do here?
Um, my guess 2, sir,
Why 2?
because like we cut before the forces, so here there's
No.
no.
Okay.
Okay.
Remember that whenever we want to do the cut, okay, we don't consider about the representative concentrated force.
Oh, I see.
Remember, we draw for the representative concentrated force is just after we finish the free body diagram. Okay, so like let's try to take a look at this one. Where are we supposed to carry that? There is no representative concentrated force there. So there is no discontinuity except for at A and at B, because at A there is AY, at B there is BY.
Yes.
So the discontinuity is only happening at A and at B. So where are we supposed to put the section?
So either, so just like cut it before B, perhaps, if we will start.
Before B, after A, right? So how many sections?
Before B, after A, 2.
Nah, not 2 sections, only 1. Before B, after C.
Oh, yes.
You understand? Because the discontinuity is only happening here and here. And one section can represent, okay, one section can represent the distributed load and distributed moment between discontinuity.
Okay, I see.
Okay, so here there is a discontinuity, here there is a discontinuity. So one section here is supposed to be enough. Okay.
Okay. So
let's take a look at this. This one, the discontinuity happening here,
okay.
and happening here because previously there is no distributed load and suddenly there is a distributed load, right?
Okay.
So because there are 3 discontinuity, then the first section is supposed to represent between this discontinuity and this discontinuity. The second section here supposed to represent from this discontinuity to this discontinuity, right?
Yes, correct.
Okay. This particular problem, how many discontinuity there? There's supposed to be at A, right? Because there is a force there. How about B here?
Yes, there is, and 2P as well.
Okay.
Then
How about B?
Yes.
How many discontinuity? 4, right?
Yes.
Okay. Between the first and the second discontinuity, this is the first section.
Yes.
Okay. Between P and 2P, there is our second section. And between 2P and B here, there is our third section. So always between discontinuity. Okay.
Yes.
Okay, let's read the break here. So do you get it, right? Why it's only one one section there which we did, right?
Yes.
Okay.
Sir, later on, in the cut, let's say we will use the cut to the B side, do we include the representative force or no?
After we cut it.
Yeah, after we cut it, then we include it.
Yes, after we cut it, after we draw the free body diagram, then we can draw the representative concentrated force.
Oh, okay.
So representative concentrated force can only be drawn after the free body diagram is drawn.
Oh, okay.
Okay, you cannot do it before that.
Okay, I understand.
Now this is the results. We have PI 480 and AY 240. So this is my free body diagram. Right, like this, triangle. Okay, here there is a 240 area. Here we have 240 lbf. Here we have 280 lbf, right?
Yes.
Okay. As I told you before, the section supposed to be here. Correct, right?
Yes.
And now we try to draw the new free body diagram for the section. Okay, the new free body diagram for the section. So the new free body diagram is supposed to be like this, right? Okay, I draw the left free body diagram.
Okay.
So I have 40 lbf. Yeah, correct, right? This.
LBF, sir?
Yeah, lbf.
So it's
Pound
okay.
force, right?
So it's the moment.
No, lbf. lbf is pound force.
Oh yes,
Not-
yes.
not-
Oh yes.
Not pound feet.
Feet. Okay, okay.
Yeah. I believe you learned about it in the introduction to engineering and design, right?
Yes, yes. I confused it with feet.
Okay. Okay, just now it's 120 pound feet. Okay.
Sir,
So, yep.
before you continue, I want to ask about location. If triangle, 2/3L is from the height ya, is from the ujung ya, di puncaknya ya.
Nope,
It's not.
no. 1/3 from the 1/3 from the maximum, 2/3 from the minimum. This one, 1/3 from the maximum, 2/3 from the minimum. So the length here supposed to be 8 feet. Here supposed to be 4 feet.
Yes, so sepertiga L itu dari sebelah kanan kan Pak?
Yes, correct. Not
2/3.
from the right side, but from the maximum.
Yes, from the maximum.
Because
ya.
the distribution can be the opposite, right?
Oh, I see. If the kalau saya kan pakai termnya alas segitiga. Nah, dari alas segitiga itu sepertiga L gitu berarti ya Pak. The maximum, I mean.
Okay, yeah, from this one you mean.
Yes.
Okay, yes.
Okay, Pak. Thank you.
Okay, this one, and what we have here is V and M, right? For the internal force and internal moment. Correct, right?
Yes, sir.
And the distance here is supposed to be X. Okay. Now, what is the maximum value here?
Is it?
Previously, it's 120 lbf, pound per feet.
So it should be 60 pound feet.
60. Why 60? It's X. This one is 12.
Because I assume we just cut it in the middle.
Nah, not necessarily. I'm not cutting it in the middle. I'm cutting it at X location from the left.
I can't find a reason, sir.
Why cannot find the reason? Because this one. Why I cut it at X? Because I want to find the distribution.
Yes.
I want to find the equation. So I cannot cut it at certain location, at exact location. So I cut it at a variable location with x variables there. Do you get it?
Yes, I understand the one.
Okay, but you cannot find the value of the maximum force, as maximum distributed force, right?
Yes.
Okay, so if the maximum here is 150 for the 12 feet like that, okay, what is the value of the distributed load at 6 feet, exactly in the middle? 60, right? Just now you answered me 60 pound per feet.
Yes.
Okay, now if I want to find out the distribution at 8 feet from the left, what is the value there?
8. Uh, is it 15? Or is it
Nah, not 50. 8 feet from the left.
15? Is it 15?
No. How
Or
can
is-
it be? In the middle is 60. Now it becomes 15.
Oh, okay. Uh, um,
Just now,
oh, wait.
why you can get a 60 there is because you put it as a half, right?
Yes.
Actually, it's not half, but we're supposed to put it like this. 6 feet divided by 12 feet multiplied by 120 lbf per feet. So what you get is 60 lbf per
I
feet.
see.
Okay, if I want to find out the distribution at the 8 feet from the left, like this, so it's supposed to be like this: 8 feet divided by 12 feet multiplied by 120.
So it's 80.
Yep, 80. Now, if I cut it at x, okay, what is the maximum? What is the distributed force there at x? The answer is like
12.
this.
Yes.
Okay. So what is the answer there?
10x.
10x.
10x lbf per feet. So the maximum here is 10x. Okay, do you get it?
Yes. See now.
Yeah, because it's supposed to be in variable x. Remember, we get it at x distance from the left.
Sir, I want to ask. So in order to get a diagram, we need to know the equation first ya Pak. Like
Yes, correct.
Gimana naik turunnya kurva itu kan
Yes,
kayak
correct.
di meter 1 jadinya nanti 10 lbf per feet gitu.
Yes, correct.
Oke, I see. Oke, Pak.
So the maximum is supposed to be 10x, right? The maximum there is supposed to be 10x. And sometimes you have to find out for the quadratic as well. For the quadratic, we have to find the equation first. Okay, for this one, the equation is 10x. The equation for the maximum at certain x direction is 10x lbf per feet. Okay, now Darian, it's still you, Darian.
Okay.
If the maximum is 10x, right? What is the representative concentrated? What is the representative concentrated force? Yeah.
Oh.
The maximum is 10x, right?
Yes.
The area under the triangle, right?
Yeah.
So what is the area under the triangle?
Oh, x times 10x. Then
10x times this, right?
Yeah, so it's
Divided by 2, right?
yeah, so it's 5x squared divided by
Okay,
2.
so it's supposed to be 5x squared, right?
Yes.
Okay, 10x times 10x divided by 2. So I just put it there in order to make sure that you understand what it is. 10x times x divided by 2. So f there is supposed to be 5x squared. Okay, Darian? You get it, Darian?
I understand.
Okay. Now, because I draw the final free body diagram, then I can represent it with concentrated load like that. Okay, Darian?
Okay.
And the concentrated load is supposed to be located at what is location?
2/3 of x.
Yeah, 2/3 of x. Or if we use the right side, it's supposed to be x per 3, right? Darian?
Yes, sir.
Okay, now let's try to find p and m.
Okay.
Using sigma fy equal to 0. What you have there?
So 240-pound force minus 5x squared minus v.
240-pound force minus 5x squared minus
v.
v. So our v is supposed to be
240 minus 5x squared.
240 minus 5x squared. So this is our v distribution. Okay, as I told you, right, when the distributed force is linear, the shear force will be quadratic. Correct, right? This one, Darian?
Quadratic. Yes.
When the distributed force is constant, the shear force will be linear. So always increase by one order like that. Now, how to get the sigma? How to get the m there?
Moment. So 200.
Sigma moment at which location?
Oh, sigma moment. At the I believe at the point, the unknown.
Yeah, I think it's better to put it here, right?
Yes.
Okay, right h. So sigma moment at right h equals to 0. Then what you have there?
So if counterclockwise positive, so 240-pound force minus 240-pound force times x.
Okay, 240 x. What else?
Plus 5x squared times x over 3.
Plus 5x squared times x over 3. What else?
I think that and the moment.
Yeah, you are missing the most important one.
Yes.
M there. Okay, counterclockwise positive equal to 0. So
0.
m equal to
240x minus 5x squared times x over 3.
240x minus 5 over 3 x to the power of 3 like this, right?
Yes.
And again, right, you can see that if the distributed force is linear, the the shear force will be quadratic, and the moment will be to the power of 3, increased by another order from the shear force. Do you get it?
Yes.
Okay, now because it's not that easy to draw this kind of curve, okay, sometimes what I do is to check at 3 locations at least. So at x equal to 0, at in the middle, x equal to 6, and x equal to 12. Okay. Phi at x equal to 0. What is the value there?
240.
40. Then phi at 120 there. Sorry, phi at 112 feet. What is the value there?
Negative 480.
Negative 480. You sure? Oh,
Yeah.
44 times 5.
How come?
12 multiplied by 12 is what?
144.
144 multiplied by 5.
Oh, yes. 720.
720.
240
So-
minus 720.
So what is the value? Minus
480.
minus 480. Okay. Exactly in the middle at p equal to 6. At 6.
6 is 60.
36, 80, 60, correct. Positive, right?
Yes.
The same for this one. Moment at x equal to 0. What is the value there?
0. So
0, right?
530. Oh, yeah, 0. Yes.
Okay. Moment at 12.
Times 12. 31,680.
31,680.
680.
Are you sure about that?
Oh, actually, no. It's not. Yes, I just realized there. It's supposed to be 0.
0 as well.
Yes.
Okay, yes, correct. It's supposed to be 0. Because there is no constraint moment there, correct?
Yes.
It's supposed to be 0. Then the last one, moment at 6.
At 6 should be 1080. So 1080.
Okay. Minus 6. Okay. So this is supposed to be the results, right? Now let's draw it. We have all the points there, right?
Yes.
We have all the points there. So this is my shear force diagram. And this is my moment diagram. Okay, the shear force diagram at x equal to 0, the value is supposed to be 140, right?
Yes.
140. And then at x equal to 6, the value is supposed to be 60,
60. Yes.
roughly here. And then at 12, the value is supposed to be minus 480.
Yes.
So roughly here. So this is your graph. So this one is 60. This one is supposed to be minus 480. Everything is in LBF. So this is your graph. You can see, right? Quadratic equation there.
Yes.
Okay. Now for the moment. 0, right?
Yes.
And then 0 again here at the edge. And then 1080 in the middle. Okay. Although it's supposed to be following to the power of 3, right? wait, I think I will check again at one location. Moment at x equal to 3 meters. What is the value there?
Moment at x equals to 3 is 675.
And moment at x equal to 9, 9 meters and 9 feet. What is the value there?
945.
945. So basically, it's like this. 675 with roughly here, and then 945 is roughly here. So most likely your graph will be like this. Okay.
Sure.
That's the moment diagram. This one is 1080, 945. This one is 675.
So I have a question. So like for this case, the normal we know is 0 already, right? So we don't have to solve or draw it.
Which one?
Normal force, the internal.
Oh,
for the
yes, you
normal.
don't have to.
Oh, okay.
You don't have to. Okay. But do you get it, Darian, how to draw this?
Yes.
Yeah, this one is supposed to be quadratic and this one is supposed to be 2 power of 3.
Yes.
Okay, good. Thank you very much, Darian.
Yes, sir. Thank you.
We still have slightly less than 20 minutes. Darian, please point out. Yeah, Rizky.
I want to ask a really simple question. At the verse, you put over 12 for the distance.
What do you mean by over 12?
When we looking for the force.
Okay, when we're looking for the distributed force, right?
Yes.
So basically, just now I'm asking Darian, right? If we want to find out the distributed force, the maximum distributed force at certain location, what is the equation? So actually, the equation, the easiest equation is supposed to be the maximum this here, the maximum that we have for the whole length is 120 lbf per feet, right? So basically, your equation, right? Your y equation, W equation, W is the distributed force. So the W equation is supposed to follow the maximum here. Okay, this one is not maximum, then just don't put it as maximum. It's just 10x. Okay, the maximum there. So W, the equation for the W is supposed to be the maximum divided by the whole length. Okay, divided by the length multiplied by x.
Pak, so 12 is the length, yeah?
Yep. The maximum is 120. So you can see it. The maximum is 120 lbf per feet. 12 is the length multiplied by the x. So it's 10x. So when we try to find out the W at x equal to 6, we will have 60. W at x equal to 8 will be 8, etc. Do you get it? What you need to do for the linear equation is just follow that. Okay? Linear equation going to the right, okay? Going up to the right. Linear like it. So basically what you need to do is just to find out the equation. Hello, Rizky? You get it, Rizky?
Yes, but the maximum here, the one 120 is given in the equation, or
it's given in the question.
Okay. I didn't see the question clearly. Thank you, Pak.
Okay. So basically, the easiest way to find out for the linear equation, right? Is W is supposed to follow this equation, AX plus B. Okay, and we know two W value there. W at X equal to 0, which is 0, and W at X equal to 12, which is 120. Okay, you can input this value to the equation, this value to the equation. So the first equation supposed to be, okay, I will just put it here. W is equal to AX plus B. Okay, the first equation is W at X equal to 0 is 0, and W at X equal to 12 is 120. Okay, so you can just put it here. So the first equation is 0 is equal to A multiplied by 0 plus B. And the second one will be 120 equal to A multiplied by 12 plus B. So in this case, B is equal to 0, and then A there is supposed to be, if B is equal to 0, then A will be equal to 10. So our equation, this is the constant that we have. Put it back there. W is equal to 10x plus 0. W equal to 10x. So this is the basic equation, right? I believe you're supposed to know about it from the high school. Correct, right, Rizky?
Yes, Pak.
So for linear, it's supposed to be that way. For quadratic, yes, we have to know 3 points. And the equation is supposed to be ax squared plus bx plus c. Like that. Any question about this?
So I have a question, sir.
Yep.
So before that, can you please go to the previous slide?
Yes.
Okay. So the free body diagram, after we cut the main free body diagram, so the length is x, right, sir? But when the x is equal to 12, when the x is equal to 12, should we take the 480 pound force on the right edge into account, sir?
If we want to draw the whole free body diagram, yes, we have to draw it like this. But the problem is, in order to represent for the section, we cannot draw for the whole free body diagram. So we have to draw it like this. Okay. When we draw it like that, we have to determine whether we analyze the left side of the cut or the right side of the cut. That's it, actually. We don't have to think about what force supposed to be there. Okay, what force supposed to be there is based on the cut that we do there. So if we use the left side of the cut, then only 120 lbf will be there and the distributed force. If we use the right side of the cut, then I will use 480 lbf and the distributed force. You get it? Hello?
Yes, sir. I mean, the x eventually will get to 12, right? From 0.
Yeah, but you don't have to think that way, because that this first cut is we represent it from the left cut. Okay, we represent it from the left cut, right? Later, it will be represented by this phi and w. So when x, okay, when x later reach 12 feet, right, the 480 lbf will be represented by v here. So you don't have to think about it. Okay, that's why you can see here the value of our shear force at x equal to 12 is the same as minus 480 lbf, right? Which is actually representing this. Okay.
I see, sir. Yeah.
So you don't have to think about it.
Thank you, sir.
Just choose which side of the kata you will use, the left side or the right side. Later, it will be considered automatically. The other concentrate force, it will be considered automatically by the V and M. There, this one, these two. Okay?
Okay, sir. Thank you, sir.
No problem. Okay, for this one, I think because we only have less than 10 minutes, I will try to make it fast. Okay. This is another type of problem. Okay, this is another type of problem. So the beam is this. This is the beam. And there is a strut here. The strut there is made to apply the load F there. Okay, and for this kind of case, because the beam in question is just this, and we define this as strut, okay? Okay, because the beam in question is just this one, then what you're supposed to do is to represent this particular force which is happening at the strut to this location. Okay, so basically we just need to draw this particular free body diagram to represent the force at this particular location. Okay, we can see that if we draw it like this, the F will be here, and here there will be normal force, then this one shear force will be going down, this one going up, shear force, and then moment, normal force, shear force. Okay, so what we're supposed to do right now is to find out for M and V there, and then so actually it's not M and V, MC and C and VC there, because we name it here as C. Okay, MC, NC, and VC there to become our external force at C. Okay, so using sigma Fx equal to 0, what we will have there is F minus NC equal to 0, where F here is 10 kilonewton. That's why this one is 10 kilonewton. So our NC is equal to 10 kilonewton. Okay, then after that, using sigma Fy equal to 0, what we will have there is Vc is equal to 0. Then using sigma moment C equal to 0. Okay, remember that the h is 3 meters. Okay, what we will have there is, if clockwise moment is positive, mc plus 10 kilonewton multiplied by 3 meters, the height, the height, okay, equal to 0. So our MC will be minus 30 kilonewton meter. Okay, minus there means that the actual moment is supposed to be counterclockwise instead. So MC will be 30 kilonewton meter counterclockwise. Then the next one, after we find out for all of these three values, the next thing that we're supposed to do is to put it at the beam here. So now our beam become like this. This is because there is a pin joint there. So AX, AY, because there is a pin here. There is roller here. There will be BY, and at C, okay, there will be a moment 30 kilonewton meter because action and reaction previously is counterclockwise. So here it will be clockwise. 30 kilonewton meter. And then we have NC, 10 kilonewton meter. It's supposed to be going to the left. Here, action and reaction is supposed to be going to the right. 10 kilonewton. The VC is 0, so it's just like this. So now, what you have here will become our external force at point C there. The next thing that we're supposed to do is to determine the value of Py, Ay, Ax using sigma Fx. This one is first free body diagram. Right? Sigma Fx2 equal to 0. This one is the second free body diagram. Sigma Fy2 equal to 0. And sigma moment 2 equal to 0. After you solve for this, you will be able to get Ax, Ay, and By. And after that, then you can solve for the problem, for the distributed force and distributed normal force, distributed shear force, and distributed moment. That's the thing. So solve for Ax, Ay, By first, then you can solve for distributed force, moment, then shear force, normal force, and moment. Like that. Okay. Omar. Hello, Omar.
Yes, sir.
For this particular free body diagram, how many sections that we're supposed to use? This one, the second free body diagram.
2.
Yes, correct. Two sections. This is the first one, and this is the second one. Because the discontinuity make it that 2 sections is enough to create the moment diagram, normal force diagram, and shear force diagram. Okay. But because the time is not enough, then try to do it by yourself to find out for this Ax, Ay, By, and distributed force and normal, shear, and moment diagrams. Okay, you can practice by yourself. But this is the way to handle if the we have to find out the external force first by creating another free body diagram, because the force there is not directly at the beam. Here the force is happening at the strut welded to the beam. So we have to move it to the beam first, then solve the problem.
Sir, so the diagram is only for beam ABC.
Yes, correct. because
Okay.
actually it depends on the question. Here, draw the normal, shear, and moment diagrams for the beam. Okay, so the beam there is ABC. Okay, loaded by the force F applied to the strut. So strut is not part of the problem, unless from the beginning it is stated that you're supposed to find the distribution at the strut as well. Okay. Matthew?
Okay, sir. So, sir, for homework number 5, which one is the compound supported beam? Is it ABC or CD?
Wait a minute. The new one, you mean?
Yeah, the new one.
The new one is for next Thursday. Number 5.
Yeah, which one is the beam that you're talking about?
The whole beam. ABC is one beam and CD is another beam.
Oh, so we make 2 diagrams. Yeah.
No, the whole. Just one diagram for the whole is supposed to be okay.
Oh, never mind. Okay.
Yeah.
Thank you, sir.
Okay. I think that's it for today. Okay. See you again on next Thursday, and please do the homework. Okay. For next Thursday, I will continue with the discussion on the distribute force, moment, distribute force, and the moment. Okay. And I'm not sure whether maybe we will end the class with a quiz like that for next Thursday. So please try your best to study by watching some of my videos in the YouTube like that. Okay, I think that's all for today. See you again next Thursday. Okay, bye-bye.
Terima kasih banyak Pak Satrio.
Thank you, sir.
See you.
Thank you, sir.
Pak.
Thank you, sir.
Sir.
Thank you, sir.
Pak.
Okay, Pak.
Yep. Bye-bye.